uh, the my goal in this video is to not come out as a teacher. Hello, myself Kaustubh Dwivedi, and today we're going to discuss the step potential part 2. And one more thing, I'm recording this video in times of in the Diwali night. So in the background there may be some crackers sound. Well, I'm recording it past 12, but still there is something going around. So you may have to face some background music, which is completely unintentional. But okay, let's do it. Okay, so in the last video we did this. I hope you remember. And this is what we did basically. And more than that, we did more than this. In the last video, we also discussed this is a coefficient of reflection, this is the coefficient of transmission. We also did something more with this, which was that we also used, let's say, we use this now, right? We set this equation to be 1 minus k2 by k1 divided by 1 plus 1 plus k2 by k1 whole square. So if we assume, let k2 by k1 to be this operator, this symbol, some call it chi, some call it something else. I don't know what we call it. Just write it like this. This form of the equation will come out to be, root over of 1 minus v naught by e. Alright. Now if we use this in this wave function, this will turn out to be 1 minus chi divided by 1 plus chi, which is nothing but root over of e minus v naught divided by root over of e plus root over of e minus v naught whole square. This is the equation of our coefficient of reflection. Similarly, the coefficient of transmission will come out to be 4. Again, you can do you can take k1 common here. If you take k1 common, it will be k1 square. This k1 square and k will cancel. This will be k2 by k1. This will be 4 chi 1 plus chi square. Okay. So sometimes in exam what happens is that they will give you this value, or they will give you this value. This value can be given in a form of equation also. That this question can be complicated, but I think it's a bit easier these days to get this question solved. Okay, this is what we did. Sometimes what happens is that in exam they also ask us questions like R by T ratio. The ratio of coefficient of reflection is to ratio of coefficient of transmission, and the ratio will come out to be root over of e into root over of e minus v naught square divided by this one, and this one will cancel. It's divided by 4 root over of e minus v naught, which is basically equal to which is basically equal to 1 minus chi whole square divided by 4 chi. This kind of questions also they ask in exams. So this is the last video which we discussed. Now, in this video we are going to discuss the second part. Second part is what? Where energy of the particle is less than V naught. That part is a bit tricky, so we are going to discuss that part. And why that part is important? Because that part is going to hint us for something greater. That part of step potential is going to give us a hint of some bigger phenomenon in quantum mechanics, which is called quantum tunneling. So it will not explain quantum tunneling completely, but it will hint you that okay, this something like this can happen. Okay, quantum tunneling is something which I'm going to do my next video on, and even when I will do my next video on quantum tunneling, it will be 2 parts. Okay, I'll explain that in the next video. Let's focus on this part. Okay. Now, this is the situation now. The step potential is as usual. It was in the first question we used the step potential, the same step potential. Only the condition here is that energy of the particle or energy of the wave is less than the step potential. Now, classical understanding, what does it say? Our classical understanding will tell you that the particle will come here and it will reflect here, it will reflect from here, and nothing will get transmitted, and that's it. That's the end of the thing, because energy of the wave is less now. How can it go through? It cannot. All right. It just to enter, the energy has to be slightly greater than the V naught. Now it is not greater than V naught. And now E can be less than V naught. E can be very much less than V naught. That also is possible. Now, in this entire scenario, what will we have to do? Okay, what will we have to do? Now, I'm going to solve it from the beginning. I mean, from the Schrodinger equation, and okay, let's start. Because if I start talking, there are a lot of things I want to say here. But let's start from the math. Let's start the math, because otherwise it will be way too much talking and little much of mathematics. Del square psi by del x square plus v psi equal to e psi. This is our Schrodinger equation. Now this is our region 1, this is your region 2. Now in region 1 v equal to 0, so del square psi by del x square is equal to 2me by h bar square psi. This is the very famous equation which we are coming to. We have solved this kind of question in simple harmonic equation also, and now we are doing this in quantum mechanics also. I have done my last 2 videos where I have also done this kind of derivation. Now this is a differential equation. How will we solve it? How will we solve it? We know how we will solve it. D square plus k1 square equal to 0. Now D is equal to what? Plus or minus I k1. Now the solution of psi will be psi 1, which is equal to a e to the power I k1 x plus b e to the power minus I k1 x. Now instead of a and b, you can also use sine and cos function, but I am not going to do it because in this kind of question we don't need that. The question in which we will need sine and cos function, we will also use that. Don't worry about it. Okay, this is energy E. This is energy E. Okay, this is coming out to be your equation for region 1. Okay, what is the K1? K1 is exactly this. I don't need to rewrite it. K1 is 2me by h bar square. Now what is K1? K1 is your propagation vector. Propagation vector of a wave gives us the momentum. Now in this wave which is psi1, what will happen? There is a, let's take a momentum vector on psi1. It will give us what? Minus I h bar del by del psi of psi1. This will give us what exactly? This will give us h bar k1 a e to the power I k1x plus minus h bar k1 b e to the power minus I k1x. Look, if you take these two to be your two eigenstates, now both these eigenstates are giving two eigenvalues. Both the eigenvalues are momentum eigenvalues, and both are showing the direction of the propagation. What is the direction? This particle is propagating in a positive direction. This particle is propagating in the negative direction. It means that your incident wave is nothing but a e to the power I k1x. Your reflected wave is nothing but b e to the power minus I k1x. As of now, I think you understand everything because I did this in the last video also, in the first part of the question. Now what happens now? Your question would be, what happens now? Okay, I was going to discuss this also. Yes, the incident wave and the reflected wave, and I was thinking of something else to tell you. I think I'm missing it. Okay, whatever. This propagation, I told you about the propagation. Yes, psi incident, psi reflected, momentum, everything is done. Am I leaving something here? Nothing. Okay, let's go to the second part. Now what happens is, this particle has to go through this. Let's not think about it and write the equation first. Okay, so equation of the wave function will be del square psi by del x square minus h bar square by 2m plus v psi plus e psi. Okay, now your v will be v naught in this region. Okay, now what will that give us? That will give us del square psi by del x square plus 2m by h bar square e minus v naught psi. Okay, very simple, very simple. Now look at this. Here we have a K1. K1 is a root over of 2me by h bar square. In the first question we discovered, we used a thing called root over of 2m e minus v naught by h bar square. Now can we use this function here? Think about it. Can you use this function here? You cannot, because if you use this, this has to come out as your propagation vector, and the propagation vector itself is coming out to be imaginary. Look at this. In this region, if we use E minus V naught or K2, this will not come out because this K2 itself will come out to be negative. So our propagation vector itself will come out to be negative. So that is not a valid, that is not a valid way to do the math here. So now what we will do, we will have to find a valid point, to counter this. So what will we do? We will just change the sign of it. We will make it 2m by h bar square whole into v naught minus e. We'll just change the sign. After changing the sign, we'll assume some new constant. Let's say nu is equal to root over of 2m v naught minus e by h bar square. Yes. So now when you solve this equation, it will come out to be like this. Okay. Now what is the solution of this? Look, this was the equation, one equation this was. This is another equation. This is another equation. Now tell me, are these two equations going to have the same solution? No, it will not. It will not. How will you solve it? The process might be the differential equation solution, the process might be same, but our method, our equation will not be same. First equation will be c e to the power psi x, it would nu x plus d e to the power minus nu x. Both are coming out to be solution. This is one waveform, this is another waveform, or wave equation, or eigenstates, whatever you can call it. This is coming out to be for region 2. Now look at this. When psi 2, here there is no imaginary points. Okay. I remember what I was trying to tell here. What I was trying to tell you here was that this waveform or this wave function which you have written, it is only written as psi x. But your wave function can be dependent on time also. So what you will do? You will write psi x and you will write e to the power minus I e t by h bar. That's all. That's all. Nothing else. Similarly, this one can be transformed into psi xt by taking psi x, which is basically this form, and multiply it with this waveform. And you know E is equal to h bar omega. So you can write it as this also, minus I omega t. Nothing is going to change. Now if we write the complete equation now, psi I stands for incident. It is nothing but e to the power I kx minus omega t. And similarly, reflected wave can also be written as b e to the power minus I k1x minus I omega t. You can also write it this way. So okay, let's come to this part. When psi x tends to infinity, now you can see a wave function must be valid when psi x tends to infinity. The wave function must be 0. Now this wave function will come out to be 0, but this wave function of c e to the power nu x, this wave function is not coming out to be 0. This wave function is diverging in nature. So we have to take solutions where c is equal to 0. We have to we will try to avoid this wave function. So now what is the psi 2 becomes? Psi 2 becomes d e to the power minus sigma x. Yes or no? This is nothing but your what? This was the incident wave, this was reflected wave, this will be what? Transmitted wave. Yes, this will be your transmitted wave. Okay, from now till now, every math is very easy. Nothing to worry about. Nothing to worry about. But the problem will arise when you will calculate the coefficient of reflection or coefficient of transmission. Now, how will you do it? Okay, look. This is your incident part wave, this is your reflected wave. When you have to find coefficient of reflection, you have to use this JR by JI mod. JR is your probability current density for the reflected wave and probability current density and of incident wave. Reflected wave, incident wave. When you calculate the probability current density of the reflected wave, you will find the result is coming out to be, this entire value will come out to be b square by a square. When you do the math, you will come out to be b square by a square. I think I have done the math. How will you calculate the j? H bar by 2 mi psi star del psi by del x minus psi del psi star by del x. Now you use this formula and you can find this will be b mod square by a mod square. Okay. Now you have to calculate also, this is psi 1. For psi 1 you can use a boundary condition of psi 0 which should be equal to psi 2 of 0. There is a boundary condition. Why we are using boundary condition? Because region 1 and region 2 are being separated by what? Your y-axis, and the equation of y-axis is what? X equal to 0. So at x equal to 0, it is separating these two regions, and the wave function must obey the continuity. That's why psi 1 0 must be equal to psi 2 0. That will give us what? A plus b must be equal to what? D. A plus b must be equal to d. Oh, okay. Don't mistake this d to be this d. This is the d by dx term. We are writing the short form of it. I hope you understand that. Now this is the part 1. Second boundary condition is the differentiation of that. This will give us what? This will give us I k1 a minus b, giving us minus nu d. Yes, yes. Now this will give us what? A minus b is equal to nu by I k1 d. Now you can transform this to be what? I nu by k1 d. Yes or no? You can do it, because you multiply I here, you multiply I here multiplying I will be minus 1, minus minus plus. This goes. Now what is coming out to be A here? Look, this is the fun part here. What is coming out to be A? A is coming out as d by 2 1 plus I nu by k1. What is B? D by 2 I minus. Got it? Got it? This is A, this is B. You can see something similar here. You can see something similar here. What is that? If you do multiply B, if you calculate B mod square, which will be B into complex conjugate of B, whatever the B and B square is, what is B mod square is equal to the A mod square, because B star is equal to A and A star is equal to B. The complex conjugate of A is equal to B and the complex conjugate of B is equal to A. You can see here. That means if this is the condition, now reflection coefficient is coming out to be 1. The coefficient of reflection is coming out to be 1. Now, if that is the case, if R is coming out to be 1 and R plus T is equal to 1, then T will be what? T will be 0. Yes? T will be 0, or if T is 0, that means there is no transmission. If the transmission coefficient is 0, I mean the wave should not transmit. That's the point which we are coming to. Yes? Okay. This is the basic math which we did here. Now we are going to do something called analysis of the probability density. Analysis of probability density. Now, okay, what is happening here? Okay, you understand all of this? You understand this part, all this part. Here R plus T equal to 1 and T equal to 0 and R equal to 1. It means the entire wave which is coming out here, all the wave will be reflected. It should not transmit. That's the point. Now, the funny part is that this is our transmission wave, psi t, which is equal to d e to the power sigma x. Yes. Now when we calculate the probability density of psi t, which is basically C psi t mod square, which is coming out to be what? D mod square into e to the power minus 2 sigma x. E to the power 2 sigma x. Okay. Now this part I am going to do in some zone, let's say here. I am going to do this part here. Okay, look it. Or let me take some other pen. Okay, look at here. This part. Psi of t is coming out, psi of t square is coming out to be d mod square e to the power minus 2 sigma x. Okay, now we have to check what is the value of d minus. What is the value of d minus? So that will come out to be our, okay. Look at this wave function. This will give us d is equal to 2a divided by 1 plus I sigma I nu by k1. Now what is the value of this? If I try to calculate d square, this is coming out to be 4 a mod square divided by 1 plus nu square by k1 square. Got it? Now this will give us 4 square k1 square divided by k1 square plus nu square. Yes or no? This will be the value. That means the probability density of transmitted wave is coming out to be 4 a mod square k1 square by k1 square plus nu square e to the power minus 2 nu x. Okay. Now what does this tell you? What does this tell you? This tells you that the probability of finding the particle, the probability density of finding the particle inside this is not non-zero. Is not non-zero. Okay. Again, it is not non-zero. It depends on what? It depends on the energy of the particle. Now look, if you take k1 square, then you took nu square, what will come out to be? It will come out to be 2m v naught by h bar square. Yes or no? Now this will give us 2m v naught by h bar square. Now what is k1 is giving? 2m e by h bar square. Now what this entire system gives us now? Now it gives us transmission is 4 a square into e by v naught into e to the power minus 2 mu x. All right. This tells you that the probability density of the particle is decreasing exponentially when you enter the surface. So means this is the potential of Vx, right? Let's say I draw a wave function, probability density. Now this is the propagation. This is the point of propagation, let's say, or this is the point of propagation. From here, the probability density will decrease exponentially, and the decrement will be dependent on energy and potential, or maybe it will decrease at the rate of this e to the power minus 2 mu x. This is the probability density will decrease at this rate e to the power minus 2 mu x. Now this is something that hints us that there is something more at this part. When E is less than 0 or E is less than V naught, there is something more, which we will explore in the next video. That will be basically quantum tunneling. Okay, so quantum tunneling works when energy of the particle is less than V naught. But the state potential means what happens is that we will figure out in this part is that it is also depending on the x. Okay, in this part the x means what? The length of the state potential. Here the state potential goes from 0 to infinity. So this now, when you put infinity at this plate or this part, the probability density goes to 0. That's why we find transmission coefficient of 0 to be in this case. But in the later case, let's say we will have a finite potential. This is a state potential, that will be a potential barrier. In a potential barrier, we will have the length of the state potential, like let's say the potential will be like this. From 0 to, let's say this point is, let's say A or D, whatever that is. In that case, we'll see whether the transmission coefficient is 0 or not. Because this is hinting us that the particle is decaying exponentially inside the state potential. But just because the length of the state potential is very big, is going towards the infinity, we are not finding particle here. The transmission coefficient is 0. This is hinting us, okay, now reduce the length and see what happens. that is the quantum tunneling. In the quantum tunneling, or we will study the potential barrier. In that, we'll study two parts. Just like that. We'll study a part where V naught is less than E, which is E greater than V naught. That is part one. There also we'll calculate, coefficient of reflection, coefficient of transmission, all this thing. Then we'll come out to the part where energy of the particle is less than V naught, and the potential, the barrier has a limited length of the barrier is given. Then we will also find these kind of a wave, probability density of a wave, this kind of a wave, but instead of x we'll have the finite length d, and the coefficient will also change. This will not be the coefficient will also be changed, which we'll do in the next video. I hope you understand this. I'm little uncomfortable because of the noise that is coming out. I hope, when I have shut down the windows, I have shut down the fans. I hope you understand. I hope the audio that is coming to my ear, it is not coming to your to you also. And I hope that it helps. And I hope this video helps. And yeah, that's it. That's it in this video. I will do the next video on quantum tunneling. I mean, quantum tunneling has got the Nobel Prize this time. I hope you know. And so the next video will be quantum tunneling, and maybe the next video will take much longer time than my previous videos, because quantum tunneling, I don't want to divide it like step potential into two parts: E greater than V part 1, E less than V part 2. So I'll take up time and I will make a complete video on that. Yeah, so I'll do it. I'll do that. Okay, so that's the part, and I hope you understand, and thank you.